Okay, dear students, myself M.R. Patil, HOD, Department of Physics. So let's get start the syllabus. So physics class 1, in which we are going to study dynamics of charged particle. So these things you already studied in the, that is PUC Science second year. So due to the shortage of time to cover the syllabus, I will not go much deeper in the basics of the, that is charged particles. So syllabus for dynamics of charged particle is charged particle in uniform static electric field applied along the direction of a particle in motion. Next, energy acquired by motion of a charged particle in uniform transverse electric field, charged particle in a constant magnetic field. So these things we are going to learn in the dynamics of charged particle. In this chapter, we briefly review the forces experienced by the charged particle in electric and magnetic fields. We shall assume that the velocity of the particle is small compared with the velocity of the light, and also the effect of particle on each other is neglected. So what does it mean? It means a charged particle velocity is very small compared with the velocity of light, we assume here. Also, we assume that the effect of one particle on the other is neglected in an electric field. So, here you can see some properties of the charged particles are, if the two positive charges are there, then they exert the repulsive force on each other. Okay, so if there are similar charges of negative, they also exerts a repulsive force on each other. But when there is a positive and negative charge, so they attract each other. So these things, these basic things you already learned in PUC Science second year. Also, how a electric field is produced, that thing also you studied. So we take an example here. In this diagram, this is the positively charged plate and this is the negatively charged plate. So therefore, the electric field is directed from positive to negative. It is shown by a green colored yellow line and it is represented by electric field E with an arrow over the head. Okay, so you all know that if the positive charge is placed in an electric field and if the positive charge is close to the, that is the positively charged plate, then it exerts force, repulsive force on this positive charge. Hence this positive charge move towards the negatively charged plate. If suppose instead of this positive charge, if we place a negatively charged particle here, then it is attracted by the positively charged plate. So therefore, it moves opposite in direction to the applied electric field. Okay, because negative plate exerts a repulsive force and positive plate exerts attractive force on that negatively charged particle. Clear? So this is the basic fundamental, so that you already know. Okay. Okay students, what is a charged particle? Whether all particles are charged in this universe? No. Unless and until we do some work on the particle, it will not get charged. You have seen many times in your school time that you take an example of comb. Take a comb your hair and take that comb near to the small pieces of a paper, then that paper is lifted by the comb. That thing you already know. Okay, so that is, we done some work on the comb so that the particles on the comb get charged. Clear? Without combing your hairs, if you take a comb near to the small pieces of a paper, then it will not lift. That is an example for the particles initially not charged unless we do some work on the, that is particle. So therefore, the particle is said to be charged if a characteristic developed on the particle which can apply a force on the other particle. So you can see here, that is when you rub the glass rod by a silk, then it will get positively charged, and if you rub a plastic rod with the silk, it will get negatively charged. Okay, so if the positive charges repel each other, positive negative charges attract each other. So in this way, the particle exerts force on the other particle. So it exerts force on the other particle. So that is, if it is a negative positive, it is the attractive force. If it is a positive positive, it is a repulsive force. If it is a negative negative, then also it is a repulsive force. So this is the basic thing you already learned in PUC Science second year. Okay. Then what is electric field? It is the force experienced by unit positive charge. Electric field is a vector quantity. It is measured in Newton per Coulomb. So therefore, electric field is represented by notation E with an arrow over its head is equal to force per unit charge, where F is the force experienced, Q is the charge of the particle. So therefore, F is equal to Q into E. Hoping that all these basic things you already studied in PUC Science second year, we will go to the next point. Here we are going to study charged particle in uniform electric field applied along the direction of the particle in motion. So you can see here, this is the positively charged particle. It is denoted by plus Q, and it is placed in a electric field, and this particle is moving along the direction of electric field. Here you can see the blue colored lines represents the direction of electric field, and the black colored arrow represents the direction of motion of a charged particle. You all know, dear students, it is a positively charged particle, and this particle is close to the positively charged plate. So therefore, positive repel each other. Hence, this positive plate exerts a repulsive force on this charged particle, and it is attracted towards the negatively charged plate. Okay. So let Q be the charged particle placed in an electric field E. The direction of the force is in the direction of the field E if the charge is positive. In the sense, if the charge is positive, the direction of the force is acting on this particle is along the direction of the electric field, from positive to negative, and opposite to the direction of the field. In the sense, now the force is acting opposite on this direction of the field when the charge is negative. Suppose this particle is negatively charged, so in this case the force is acting towards the positively charged plate. Okay, so therefore force is equal to charge into electric field. When the field is applied, the particle is accelerated uniformly in the direction of electric field. Then from Newton's second law, force is equal to mass into acceleration, that it is equal to, from our relation, force is equal to Q into E. So therefore it is equal to Q into E. We also know that acceleration is equal to, that is from this expression, A is equal to Q divided by M into E. Okay. So acceleration is what? It is the rate of change of velocity, or dv by dt, or d square r divided by dt square, where r is the vector which represents displacement. So therefore d square r divided by dt square is the acceleration. It is equal to q divided by m into e. We call this equation number 2. Integrating this equation, so therefore integration of d square r by dt square is equal to integration of q by m into e. So what we get? dr by dt, so that it is nothing but rate of change of displacement. It is equal to velocity, and it is equal to q by m into e into t. We are integrating with respect to t, so therefore we get t plus there is one constant, that is c. It is known as the constant of integration. When t is equal to 0, at time t is equal to 0, v becomes equal to u, that is the initial velocity of the particle. So therefore, when you substitute t is equal to 0 in this expression here, so this term get 0 and v becomes equal to c. So you can see here c becomes equal to u because v is equal to u. So therefore, equation 3 becomes v is equal to q by e divided by m into t plus u. Call this equation number 4. Again integrating equation 4, we get, that is integration of the velocity term, it becomes the position vector r, that is equal to q into e divided by 2m into t square, as we are integrating it with respect to time, and u is the initial velocity, so we are integrating again this also with respect to t, so you get ut plus c1, that is the integration constant. Okay, so when t is equal to 0, suppose the position of the particle is given by r naught. In the sense, in the electric field, the position of the particle is represented by r naught. Then at t is equal to 0, this term becomes 0 and this also term becomes 0. So r becomes equal to c1. So that position vector we represent it by r naught. So therefore c1 becomes equal to r naught, that is the position of the particle. So therefore equation 5 reduces to r is equal to qe divided by 2m into t square plus ut plus r naught. So you can see here, see this is the total displacement of the particle in the electric field, then that is equal to ut plus half qe divided by m into t square, ut plus half at square, it is like this. Okay, the equation 6 is applicable. This equation 6 is applicable in general, whatever may be the direction of r naught, u and e, that is initial velocity and electric field. So the equation 6 can be represented by vector diagram is as shown in this figure. So therefore, if the charged particle is placed at rest on the origin of the coordinates, in the sense, here you can see, if the charged particle is placed at rest at this position, origin of the coordinate, then initial velocity of the particle becomes 0 and the position coordinate of the particle becomes r naught also equal to 0. So therefore, then the equation 6 becomes r is equal to qe divided by 2m into t square. We call this equation number 7, and from equation 4, v is equal to q into e divided by m into t. So we call this equation number 8. So from equation number 7, we get the position coordinate or the position vector of the charged particle, and from equation 8, we get the velocity of the charged particle in an electric field E with the charge of the particle is Q. Okay, now energy acquired by a charged particle. So the field imparts energy to the particle. The force is given by F is equal to Ma, or it is equal to Q into E. In the sense, charged particle is inside the electric field and it is moving, then that field exerts some force on this charged particle, hence it acquires some kinetic energy. So that energy is known as the energy acquired by the charged particle. So the work done by the force in moving the particle is given by, suppose the particle is here and it is moving from position 1 to position 2 when the electric field exerts a force on this charged particle. that can be calculated by work done is equal to, that is from point 1 to point 2 it is calculated by, that is m into 1 to 2 acceleration into dl. As we know, force is equal to, that is work done is equal to force into displacement, and force is nothing but mass into acceleration. So mass is a constant here. So therefore we are integrating it from 1 to 2 position, acceleration a into dl. Okay. And also acceleration is equal to rate of change of velocity. So therefore we can also write the velocity as dl by dt, rate of change of displacement. So therefore dl is equal to v into dt. So we substitute these two values in the equation number 9. So therefore w is equal to m into 1 to 2 acceleration as dv by dt and dl as v dt, v into dt we substitute here and we integrate it. So it is equal to m into integration of, that is dv by dt is the acceleration, it becomes v and dv. So because dt get cancelled. So therefore this is equal to integration of v is v square by 2, so that it is equal to 1 by 2 m v square from limit 1 to 2. Okay, so call this equation number 10. If v is the potential difference between the points, that is 1 and 2, if v is the potential difference between the point, then we know one expression, work done is equal to g into v. Okay, so call this equation number 11. So thus w is equal to 1 by 2 m into, that is, it is not a g, it is a q, w is equal to q into v. So therefore thus w is equal to 1 by 2 m v2 square minus v1 square is equal to q into v. So call this equation number 12, where v1 and v2 are the initial and final velocities of the particle. Therefore w is equal to q into v. So thus w is equal to 1 by 2 m. We are substituting here limits from 1 to 2. So therefore v2 square minus v1 square into q into v. If the particle starts from rest, then v1 is equal to 0, that is initial velocity. So therefore w is equal to q into v is equal to 1 by 2 m v square, where v is the final velocity. So therefore v is equal to square root of, therefore v is equal to square root of 2qv divided by m, or v is equal to, so q square e square t square divided by m square. Okay, from equation 8. So therefore kinetic energy is equal to half m v square. Substitute this value in this expression. So half m q square e square t square divided by m square. So 1 m get cancelled. So therefore r, and also from equation 7 r is equal to q e divided by 2 m into t square. When you substitute this expression in the above equation, so we get kinetic energy is equal to q e r, where q is the charge of the particle, e is the electric field, and r is the position vector of the particle. Okay, thank you.